thank you for joining us today on the presentation about It Wasn't Me, Attacking Industrial Wireless Sensor Mesh Networks. I'm Erwin, this is Matthijs. We're both from the Netherlands. As you can see, we had two options to come here. We didn't take the car, but Google actually showed two ways, and I thought it was nice to show how far away it is by car. But we're here to actually discuss something about wireless sensor networks, and specifically two protocols, wireless HART and ISA 100. Anybody is familiar with those protocols, has heard about them before? Any hands? Yeah, one in the back. Okay. Okay, so it's quite new to you all. Okay, that's good to know, because it's actually being used a lot in this region as well, in oil and gas fields. And so, but I think it's good to first look at the sort of industrial revolution that took place. So we're talking here about ICS systems, and specifically oil and gas fields type of systems, and they used to have like air pressure system, pneumatic logic systems, and then they moved over in the 1950s to actually do electrical analog current loops, and then they started developing further, and they introduced the digital protocols, so HART, Fieldbus, Profibus. And at some point I thought, well, we can maybe also do this without the wires, because I mean, all those devices have to be hardwired in the field, so it's actually quite costly to have all these wires in place. So they thought, well, let's develop wireless mesh networks, and we don't have to have all those wires. And that's why they created wireless HART and ISA 100 in 2007 and 2009. And if you're wondering, well, what does it look like in practice, you see on your right, you see actually a pipeline, and you see a couple of blue devices there with a small antenna. Well, that's a typical wireless HART device. ISA 100 looks similar, and that could be, for instance, a pressure transmitter or a flow transmitter. This is not the first presentation on this subject. There has been other people. It started off in 2009 already, when somebody with an academic background looked at the protocols, in this case wireless HART, and already saw some security issues with the protocol. So those have been documented already for a while. Then there was a while there was nothing, and then actually a Dutch student actually took it upon him to look at wireless HART as well, and he also has released his thesis paper, which is available as well. But he had a lot of issues because there were not many tools available to actually look at those protocols, and he tried to actually develop something using software-defined radio. I hope you're all familiar with software-defined radio. If not, Transmicro actually has a CTF about it, so then you can get some experience as well. But basically, you define the low-level logic radio blocks in software, and you have to demodulate the signal yourself. It actually can be quite cumbersome to do this for a more advanced protocol, what we're looking at right now. So actually, he didn't really succeed in being able to communicate with an existing wireless HART network. So we also did research, which was presented earlier in Miami at the S4 conference, where we looked specifically at wireless HART again, and how you could attack wireless HART. We not only looked at the protocol, but also the implementation, so the devices, and we mentioned some earlier research further on in the presentation. Again, at the S4 conference, there was a denial of service attack on the same protocols, and that again was done on SDR hardware. But basically nobody released his tools publicly. So basically we're still back at the position that there are no security tools available to actually test these networks. And I'm not sure if you have heard of Joshua Wright, and he has something that's called the Wright principle, and he says, well, basically security does not improve until practical tools for exploration are available to actually research those protocols. So we took it upon us to see if we could develop something to actually make that more practical. Just a little bit of background, what type of systems we're looking at. We're looking at industrial processes, so control loops. And in a typical system like this, you see a feedback loop. I don't have a pointer, but on your right, you see, for instance, a flow transmitter. So there's fluid going to the pipeline, and that's actually measuring the flow, and that's sending a signal back. It's the arrow going up to the left. And it's actually measuring process value. So it's reporting back, I'm measuring this flow rate. And typically that's the link that's being implemented with the wireless protocol. So it's more about monitoring, measuring. And it actually goes back to a controller. And that controller has also set points. It will actually compare those values. So it will compare the process value with the set point. And if they're not in balance or it's not within range, they actually control the valve, which is also on the pipeline, and actually change the position of the valve so that the flow rate changes within the specs of the process. So that's the typical feedback loop you have in these processes. Regardless if it's wireless or not. And then, some introduction about wireless HART. It's based actually on the HART protocol. Anybody familiar with the HART protocol? Hands? No, it's hard for me to see, but okay. So basically, the HART protocol is an older protocol which was originally developed by Rosemount, and that's also being used on the wired connections. So basically, they took the same HART protocol, and instead of the wired connection, they transformed it into a wireless protocol. So that became wireless HART. So the top layer is actually the application layer. It's actually this exact same protocol as has been used for many years. Luckily, and that's not that common in ICS world, they do support encryption in the protocol. So that's a good thing, but they do support AES encryption. And of course, that's symmetric encryption, so always the first question is, where are the keys? Because, I mean, you need to have a shared secret, you need to have a key somewhere, and that's what we looked at earlier already as well. The wireless technology is actually based on a time-synced mesh protocol, which was developed by Dust Networks, which is now part of Analog Devices. But they actually provide a radio system on a chip for the various vendors. So although you see a lot of different vendors on the slide, like ABB and Siemens, they usually all use the same radio sock, at least from what we've seen in earlier research. And if we look at ISA 100, it's a bit different. It actually relies on several standards. So it's a common, so 6 low WPAN, which is actually a mix of IPv6 and UDP. So it has a bit different protocol stack. And it's also able to tunnel other protocols. So for instance, if you have HART, you can tunnel that over ISA 100 as well. It's mainly developed by a company called Nivis. And there's actually multiple vendors who provide the chips. So there's the radio socks. There's a couple of them. So typical topology, what does it look like? Well, all the way at the bottom you have the field devices. So those are actually the devices measuring the values like the flow, temperature, etc. And you have two variants. So you have the field device, which is already a wireless HART or an ISA 100 device, or sometimes you have the traditional field devices who are still wired, but they have an adapter to actually transmit the signals wirelessly up to the gateway. So that's a gateway, network manager, and security manager. There's usually just one device. And for instance, on the right side, you see a device from Emerson Rosemount. This is what a wireless HART gateway looks like. So it's those are devices that are being used in the field. So it's all a lot of metal, water resistant, even explosion resistant. But those gateways are actually hooked up to the plant automation network, and those will send the information upwards to the rest of the applications that are running on there. And basically, the field devices itself are able to create a mesh network. So they have redundant paths, and they can forward messages for other field devices which are out of range of the gateway. Well, if you look at the protocol stacks, you actually see that wireless hard and hard are very similar. For the top layers at least, and of course the lower layers are different. So for the hard we use the analog and digital signaling over hardwired connections. But for wireless hard, of course, we have a common base layer, both ISO 100 and wireless hard. There's 802.15.4, which is also used by protocols like Zigbee. So there's multiple protocols who actually use the same lower layer. So at the data link layer and physical layer. And that makes it also interesting to look at those lower layers and see what the common denominators are actually, because both the protocols use 802.15.4, both use the 2.4 gigahertz band, and both do something which is unique to these protocols. That's actually do time slotted channel hopping, and what that means is that they will actually hop over different frequencies, different channels. And the reason they do that is that in the environments they're being used, there's a lot of metal, there's a lot of industrial systems, and there can be a lot of interference from those devices. So by hopping the frequency, you minimize the interference. And also you can have reflection. So if you have radio signals that bounce off another object and actually come back to you, you can have the same effect as a noise cancellation headphone. Basically, if you have one wave that is actually at the top and the other one is at the bottom, they cancel each other out. And that's another thing they try to minimize by hopping the different channels. And both actually have the same centralized network and security manager, which orchestrates the communication between the nodes. So for instance, that device will send out a sort of beacon similar to Wi-Fi to actually announce that there is a network. It will also say what time slots are available for a device to use. And Matthijs will tell you a lot more about that part. But first, we concluded well, okay, there's enough similarities here to actually develop a common sniffer maybe for both protocols. Well, that would be nice. Instead of one protocol, we can look at two protocols. So that's what we try to do. But of course, there's also security involved and encryption. Both use the same type of encryption, and they do it at the data link layer, where they only check the integrity and not the encryption. But at the transport layer, they do use encryption, and they actually have a join process where they actually have a handshake with the network manager to transport the keys, which could either be a shared secret, so passwords basically, or certificates for ISO 100. Actually, there's a lot of keys involved. Some of them are actually well known, as in they are written down in the spec, or they're just for authentication. And some of them actually are generated during the join process. If we look at the following slide, it becomes a bit more clear. So if you again look at the OC layers, you see that you have at the data link layer, you have the well-known on-network key, which is just used for authentication. And you have, during the join process, you have a join key, which is then again used to generate a broadcast session key and a unicast session key. And those are actually being used to encrypt the data and not just authenticate. So for ISO 100, I'm going to be very honest. The spec for ISO 100 is a bit unclear. There's many different keys involved, and it's not. I mean, this is as we understand it now, because we've We've read the spec multiple times, and it's still not completely clear how it works, but they have a division in a provisioning phase and a joining phase. And during the joining provisioning phase, they have a global key, and at the transport layer they have already a key, K open and K global, which are actually known keys. So they're documented what these keys are. And after the provisioning phase, they generate joining keys, somewhat similar to wireless HART. But as you can see, there's more keys involved here, and we still have to figure out all the exact details because, like I said, the specs are not very clear. But the question is, how do you obtain the key material? Well, there's default keys. Some of them are documented. We've collected some keys over time, and we've seen that some of the documentation also disappeared from the internet, but they used to be just available in documentation. And another thing is that for ISO 100, you can also provision over the air. And in the spec, they actually warn you that over-the-air provisioning, because the keys they use are well known, you can actually decrypt the traffic and you could sniff the traffic. So it's kind of interesting that, I mean, if you're going to do over-the-air provisioning for ISO 100, you probably want to do that in a sort of secured environment and not in the field where somebody could be sniffing your provisioning process. And we also looked at in earlier research, we looked at the actual transmitters for wireless HART, and actually it turned out that the radio SOC had a debugging interface enabled, which allowed you to dump the firmware through JTAG, and that way you can recover the keys from the device memory. So that, I mean, of course, you need to have physical access, but that also means that you have to be careful. For instance, if you decommission these devices, or if you have a device in the field which goes missing maybe for an hour and then suddenly comes back. I mean, those networks are mesh networks, and due to the weather conditions, I mean, it could change that it could happen that devices are just gone for a while. But who knows what happened in the meantime, because you can actually open up the devices and dump the key from memory. So, I mean, if you decommission those devices, and they might end up on eBay or the local equivalent, always be aware that there might be key material still in the devices. So here's a couple of wireless HART default join keys. As you can see, the first one is of course it's the hexadecimal value, but if you actually convert it to an ASCII, you see it says DOS networks rock. Well, you can now understand where that one is coming from, and multiple vendors use it because they all use the same radio SOC. The second one is not readable, but it's at least it's not ASCII, so it's for Pepperell and Fuchs. They use this key. And the third one is kind of interesting, because if you have an Emerson wireless HART gateway and you reset the device to factory default, this is the keys you get. And what you notice is, although it's not a static key, is that there's a lot of zeros in there. So it could be either sort of time-based or based on some information, but they greatly reduce the key space here, because I mean, if you know there's a lot of zeros, you can just skip that part. And yeah, I mean, so it never used the default key generated by an Emerson wireless HART gateway. And sometimes it's just the vendor name as the last one, which is an Eschenhauser. For ISO 100, we haven't located yet any default keys in documentation, so that's still something we have to look into if we can find those. So then we started looking at what hardware we could actually use. Because, I mean, yeah, we need a combination of hardware and software to assess these networks. Well, there's a commercial device called BeamLogic. That's actually the largest device all the way on the right, which sort of solves the channel hopping by simultaneously sniffing on all 16 channels. So basically it has 16 radios and sniffs them all at once. So you don't have to hop over various channels. They have a basic Wireshark dissector and no injection support, so it's sniffing only. And it's actually quite expensive device compared to the others. So we've used it during our previous research, but we weren't really happy with the results. So we started looking at other options. The first one we looked at is the Admiral RC Raven USB stick, which is also used by Killer Bee framework for sniffing ZigBee traffic. It can only listen on a single channel at once, like many of the other devices. So you have to do something with the software to actually hop on different channels. But the problem is that's a bit older USB stick. There's no free IDE anymore. There used to be Atmel Studio, but nowadays it's hard to find. It also reached end of life. And it's only 8-bit AVR chip, so it's not the fastest chip around, so we thought we better look at other options. So then we moved to the NXP B kit. Again, single channel, standard firmware, which is not open source, interestingly, but that one also reached end of life. So we started with this stick, but soon decided, well, there must be other options. So then we actually found this one, which is also from NXP, but it's a newer device. By default, it can already sniff on one channel. So 802.15.4 on one channel with the standard firmware is no problem. It's still actively supported. There's a free IDE available. It's quite powerful, the microcontroller. So it has a Cortex M1, M0 Plus. And it has the possibility to actually connect an external antenna. So it's, although the connector is not on the device by default, you have to solder it yourself, and it's actually quite small. So either very steady hands, or you need to find somebody with a rework station who can help you. But it allows you to connect an external antenna and extend your reach. So yeah, wire driving could be an option. Also, the firmware flashing is quite convenient, possible via USB mass storage, which is with something that's called OpenSTA. So from the IDE, you can directly connect to the stick and publish or push your new firmware onto the device, and that's a lot easier than some of the other solutions where you have to use JTAG to program the device. And there's actually reasonable documentation available with examples. There's a few omissions here and there, but it's interesting. Well, there's enough information there. And they also come with a protocol analyzer software, so you can sniff already on one channel. It also does Bluetooth Low Energy, so that's the channels you see at the bottom. But it can already sniff at the different 802.15.4 channels. I'm just going to show you a small video if it runs. Yeah. So what you see here is actually that we select a channel to listen on, and they actually have integration with Wireshark. So they created a local network interface. And now you can see that we can sniff the traffic. We see this 802.15.4, but there's no dissector for the data. So although we can see the packet, you can either decode it by hand, or we need to develop something to be able to see the packets.
All right. So yeah, we decided to start using this hardware as a basis for our toolkit. The nice thing about this USB stick is that it's detected as a COM device, so basically a serial port, and you talk to the device using a serial protocol, and that is called FSCI, or Freescale Serial Communication Protocol. And using this API, you can put the device in promiscuous mode, much similar as Wi-Fi. So you can sniff out all the packets on a single channel. So that is part of the default firmware. There's also a host SDK available with some examples to use this API. We face a challenge with these protocols because we need to do some advanced things. Actually, the channel hopping problem is a hard problem to solve, especially when you communicate over serial line. It is too slow to keep up with the hopping pattern of ISO 100 and wireless HART. We had to create new firmware actually to keep in pace with the hopping patterns. So if you take a look at how this USB device is constructed, actually it has two chips on board. One is the KW41Z, that's the heart of the solution. So this is actually has an integrated radio chip. The other one, the K22F, that's mainly a USB to serial converter. So that's not really interesting for us. So this is the hardware as a basis for the toolkit, but of course we need some software. As you saw in the previous demo, you only have decoding up to the 802.15.4 layer of the protocol, and of course, as you see in the OSI model, there are some other layers that we need to address. So we thought that the easiest way was to use existing tools as a basis, and we found Killer Bee to be suitable to do that. So it's relatively easy to extend. So the first step is to actually develop a driver support for Killer Bee, and the second step is creating a SCAPI dissector. Of course, if you want to get this adopted by the masses, you need a Wireshark dissector as well. So that was our plan, and I will show a short demo how we can use a combination of Killer Bee and Wireshark to actually sniff these packets. And that should... No? Oh, okay, there we go. So here are we running ZB Wireshark, which is a build of which is an existing tool, and we sniff on a particular channel. And also here in action you see that we can decode the ISA 100 protocol. And what you actually see here is advertisements that are broadcast by the network. And the fact that we can see this on channel 19 in this case is because the protocol works like this, that it will send these advertisements on all channels. So the protocol is hopping all the time. So if you want to see anything interesting, more interesting than these advertisement packets, if you want to capture actual data, that is the data that is being transmitted between the sensors, the transmitters and the gateway, for example, or the transmitters to transmitter communication, you actually have to tune into the channel hopping pattern. So you need to set a certain channel at a specific point in time. As you can see here, this is basically how it works. You have a repeating pattern of channels you need to tune in. And so what you saw here, the repeating pattern is called a superframe in the standards. And these superframes can have different periods, so between 512 and 4096 slots. So the difference between wireless HART and ISA is that they use a different time reference. So when you start a wireless network, that means when you start a gateway, network manager, it starts counting frames, and that's called the absolute sequence number. And the IS 100, regardless of when you start it, it will always use atomic time as a reference. And that starts in January 1958. So in each time slot, to understand this, we noted that this is defined as a superframe consisting of multiple time slots. A time slot denotes a communication link between two devices, two nodes within the network. But actually, you can have multiple superframes defined at the same time. So one device can talk to another on channel 15, and at the same time, within the same time slot, two different devices can talk on channel 3, for example, without interfering. So if you want to sniff this traffic with a device like we do, that can tune only to one channel, and you have to make a decision which communication link you want to follow. Unless you have a sniffer that can sniff on, has multiple radios and can sniff on all these channels together. So if you zoom in on a time slot, actually you have in the first part of the time slot a sensor or a node in the network is able to transmit, and in the second half the other party sends an acknowledgement. So that's all happening in the same time slot. So we face the challenge to actually implement this, and this turned out to be pretty hard actually. Serial communications is not fast enough to keep up these hopping patterns because the time slots are 10 milliseconds. So it's changing quite rapidly. And yeah, we need to turn to the firmware to actually accomplish this. The encryption and authentication challenge, well, that could be resolved on the host because hosts are powerful enough to do the encryption afterwards after the packet has been captured. And actually, if you want to communicate, you can do the encryption part on the host and send it along its way to the firmware, and it will transform the frame onto the radio waves. So that should be doable. The existing tools, Scapy is a fantastic tool where you not only can decode packets but also transmit packets. So yeah, that perfectly fits into our tool set. So back to the firmware. We tried different approaches and failed miserably a few times. So when you take a look at the development kit for this NXP device, you have support for real-time operating systems and for bare metal schedulers. So it turned out that a real-time operating system is very good if you need to have your code executed on a particular time. But it turned out that it required too much overhead to actually follow this hopping pattern. So in other words, I know what slot a certain communication takes place. Yeah, my code gets called, but I need to process this packet because in an advertisement frame there is information that I need to parse to discover communication links that I'm interested in. And next, I want to tune in to that communication. But it turns out that there's another task that is responsible for reading a serial communication, and that is missing the packets. So that failed miserably. So we turn to the bare metal task scheduler, which is very fast, which is a plus. And it works basically like a task is defined as a function with an endless loop. The first thing it does is call another function, the event wait function, and basically it hands control to the scheduler. And it basically says, wake me up when you have an event for me, like a packet waiting. And as soon as the task scheduler wakes you, you get into the next piece of code. And there is where you are totally responsible. Your code is running, but you need to finish your code with, say, 2 milliseconds, or otherwise you will starve other tasks, which is, again, really bad, because the serial communication or other critical tasks will not run. So, summarized, bare metal uses cooperative multitasking, and the RTOSes use preemptive task scheduling, which means that every piece of code can be interrupted by the task scheduler, and you have a lot of mechanisms you need to use to get to solve synchronization problems. So, from an architectural perspective, the firmware consists of the framework code that is generously provided by NXP. And on the right, you see the part we had to code ourselves. So for ISO 100 and wireless HART, that means that we have to listen into advertisements, and the advertisements contain the necessary information. It provides you a list of channels that are available, and time slots you need to tune in for certain communication. So now the challenge is, how do we actually synchronize? And as I said, the timing is critical. So, and it's impossible to tune into every single time slot, because you don't have the time. So, to give you an idea how this works, here are a few formulas for wireless HART and ISO 100, which are somewhat similar, but have some tiny differences. But the idea is that you have to do this calculation every time you want to tune into communication. So we decided to cheat a little bit. So what you see here is the actual the actual channel hopping pattern. And suppose we're interested in a certain communication between two nodes, and you know that in advance that it will take place at a certain time slot. You can tune into the channel in advance and just wait until time passes, and you will capture the packet. Next, you switch to the next packet you are interested in, and you can tune in advance. And yes, surprisingly, well, not actually, it's not actually surprisingly, but it turned out to work. So I'll give a brief demo. So we're firing up ZB Wireshark again. And we hacked in channel 0, which means that we activate channel hopping. And as you can see here in Wireshark, we're picking up more advertisements because these are on different channels. Actually, Wireshark does not show you that information, but here on the console you see the different channels that it's hopping now. So yeah, by using this strategy, we're actually able to interact with the network. And that's what we need to assess this type of networks. So sniffing is fine, and sniffing all traffic is amazing if you have a beam logic device, but still you're not able to actively engage with the network. But yeah, using this channel hopping strategy, you actually are able to do that. So what can we do at this point? So assuming we do not have any key, so we cannot do decryption. Well, there are a few documented attacks already. So one is signal jamming, just by blasting radio waves on a certain frequency. Yeah, you can do that as well on all channels, and yeah, probably your network will die. You can do this a little bit more surgical by tuning into particular communications. For example, if you're interested in jamming the communication between one particular device and the network gateway or another device, you can do selective channel jamming. Another idea is to join the time slots which are used for devices that want to join the network. So that way you prevent new devices to communicate with the network. And another idea is to send fake advertisements. The advertisements are not encrypted. They are authenticated somewhat, because advertisements are always authenticated by the same well-known key. So it's easy because these are just documented, and you can create valid packets that are actually picked up by the devices. So we'll show you a variation on this one, and that's that we are actually jamming the advertisement slots. So you can imagine if you have a network where sensors are transmitting data, they need these advertisements to actually synchronize the clock. So if you remember, I talked about the absolute slot numbers. These are calculated by the device over and over again. If they don't receive these advertisements, believe me, the network will die. So this is another variation we came up with, and I want to show you a brief demonstration.
Yeah, so what we have here is actually a gateway who's transmitting the... Yeah, we actually do have a gateway here that is transmitting advertisements, and on one device we are listening into these advertisements, and on the attacker machine we start a jammer. And this one tunes into the specific time slots where these advertisements are sent. And we switch back to the victim. And at some point, you notice that you don't see any advertisement packets anymore. It goes silent. There you go. Yeah, while the gateway is still running and all.
The gateway is running, but the devices are not able to synchronize with the network anymore. And yeah, you will basically achieve a loss of view on your network. So, one step further, if you manage to actually join the network, so if you grab a key by means of the previous methods we described, like over-the-air provisioning by ISA 100 or extracting the firmware, extracting the keys from firmware, then you can do a lot more. One attack is called Non-Substation. So the way this works is that if a packet is encrypted, it uses ASCCM, so that's it. That is it's counter mode, and actually that is initialized by using a nonce. So it feeds the AES algorithm. This nonce is predictable. So it contains, for instance, the network address of the sender, and it contains the counter or the absolute sequence number. So that feeds the AES algorithm, and at the end, the message integrity key, mic is calculated, and if the mic is accepted, of course, the device will act on that. So if you manage to craft a packet and it just contains an absolute sequence number that is way higher than the current state of the network, that means that the network manager will decide, okay, this is the latest ASN number. So anything which has a lower value than I currently have received, I will ignore. So that means that valid transactions will be rejected. The ultimate goal, of course, is to spoof measurements. So if you are able to manipulate a process value, then indirectly you will influence a control loop. So say that you have a set point on a vessel with a pressure of I don't know what. And if you manage to say, well, the pressure is too low, some compressor will kick in and boost the pressure. But if you can imagine what happens if the pressure is already high, things will go boom. So, what can we conclude? We're merely scratching the surface here. So we achieved our goal of creating a basic tool set, but it's just a start, actually. So we are interested in other researchers who would like to join our efforts in creating tools to actually do attacks on these networks. We have a kind of recommendation for users of these technology. Because this is protocols in use, or these systems are in use for more than 10 years. Asset owners are getting quite confident in this technology because nobody has broken it yet. So you see a trend that these wireless networks are not only used for sensors, like the transmitters, but also for control systems, so sending actual control signals to actuators and stuff. So we would recommend to reconsider that, because we feel that the first cracks are already visible. So what we like to do is expand this tool set, so implement more attacks that are already theoretically possible. Another interesting thing is that we would like to try to force devices to rejoin the network. So what that implies is that a sensor will resend an encrypted packet that is encrypted with the join key, which gives us a great opportunity to do several things. You could think of offline cracking of that handshake, but also attacks like having a device connect to a fake gateway. So you can create a sort of man-in-the-middle attack. Mapping locations is another thing. We found a colleague that was good at soldering, and he soldered this tiny connector on one of our USB devices. And we have a good antenna, so we are keen on putting this into practice and go actually do some war driving. And of course, as always, this unexplored area of vulnerabilities in the actual devices, like the transmitters themselves and gateways. How do they respond on invalid packets? So actually you can start fuzzing. Well, you can imagine if you have SCAPI and you can forge packets, the possibilities are endless. So that concludes our talk. Yes, if you're interested in this area of research, or if you're actually using this technology, please feel free to come to us and have a chat.
Do we have any questions?
So if you have any questions now, we have more than enough time to answer them.
Yeah, or if you feel more comfortable doing it not on stage, feel free to approach us later, of course.
Do we have any questions from the crowd?
Nope.
Oh, yeah.
Yes.
Yeah.
Good afternoon.
Hi.
Hi, my name is Saeed. I'm from Dark Matter, from the education section. The question I have is, you're talking about time slot hopping. Is that the same thing as frequency hopping?
Yes.
And the time slot hopping, is it only in a single channel or across the whole 2.4, the gigahertz spectrum?
Okay, this is the same as frequency hopping, exactly. So there are 15 available channels for both wireless hard and an ISO 100. And the hopping pattern needs to be calculated. It's not a static pattern. So that's what it makes it so complicated. So it's using all available channels at high speed.
Thank you.
It's just a follow-up. Since it's a really true frequency hopping, how, based on your tool, you mentioned about a synchronization, and that's how you manage to kind of interfere with the signal and block, actually. So it's more like denial of service, isn't it?
Denial of service is one of the options. Actually, because we are able to craft packets, we are able to actually interact with the network. Currently, we have just the basics in place, but as we have this foundation on SCAPI, it's relatively easy to implement the application logic as well. And you can do that comfortably in Python on your host system. Does that answer your question? All right.
Going once, going twice. And thank you, everybody. Thank you, Matthijs and Erwin, for your talk.
Thank you.
Welcome.